Hello students, this is Module 11, which covers Chapter 9 of the Lawrence and Adams textbook, and it's about independent groups designs. There's a large section of this chapter as it relates to one-way ANOVAs that we're not going to cover, so watch carefully towards the end of the video for the pages of the textbook that you do not need to read. Chapter 9, Module 11, begins with this talk of correlational design. Correlational design is a type of study that tests the hypothesis that variables are related with no manipulation of the variables. All you're doing is you're looking for a correlation. Causation is completely separate, as we've mentioned, and when you're looking at a correlational design, you end up looking at a predictor and an outcome. The predictor is the variable that is used to predict the value of another variable, and a term used instead of independent variable in a correlational design. An outcome is the variable that is predicted, and a term used instead of dependent variable in a correlational design. I do not subscribe to this thinking that Adam and Lawrence follow, in that you can't use dependent variable and independent variable when you're talking about a correlational design. Instead, I speak very, very clearly between what is, I believe, a correlation and what is a causal link. An example of a correlational design is comparing two independent variables. The predictor would be as they used in the textbook, chocolate eating habits. Does the participant eat chocolate daily or not? And the outcome would be an IQ score, for example. So is there a correlation between how much chocolate you eat in a day and your IQ score? And it speaks about this, and you're not looking as to whether one causes the other, you're just looking at whether there is a correlation. And in that regard, it helps to say this is the predictor, this is the outcome, because that's what you're looking at, and specifically, and nobody will confuse it then that you're talking about a causal link. Quasi-experimental is a type of study that tests the hypothesis that an independent variable impacts a dependent variable. The independent variable is manipulated, but participants are not randomly assigned to condition, which means that it's quasi-experimental. Using the chocolate eating example, an example of quasi-experimental design would be that chocolate is eaten before a test, and the test score has a different outcome. An experimental design, which is purely experimental, is a type of study that tests the hypothesis that an independent variable causes a change in a dependent variable. The independent variable is manipulated, and participants are randomly assigned to condition. So the simple experiment is an idea where the independent variable has two conditions, and the dependent variable is measured on an interval or ratio scale. This is what we used in assignment number 3, and also in the midterm you saw examples of this. As it related to sexually transmitted diseases, going up or down as it related to whether the students had Title V abstinence-only sex education or whether they had science-based sex education. 3 requirements then for an experiment, and this is only for the third of the 3 options that we just covered, is that there is an independent variable that is manipulated, participants are randomly assigned to a level of the independent variable, and a dependent variable is measured to test for the effect of the independent variable. Designing a simple experiment, if you want to maximize the power of the experiment, then you have a strong manipulation of the independent variable, or extreme levels of the independent variable, or you have an incredibly homogeneous group of participants and you want to increase the number of participants. If you want maximum internal validity, on the other hand, you want to eliminate all of the you want to focus on eliminating the confounds. You want to conduct a pilot study to make sure that the direction you're going is affirmed, and you want to reduce the demand characteristics by conducting a single or double-blind experiment. These are things that were covered off in Chapter 8. If you want to design a simple experiment, once again, you ensure that the independent variable manipulation is reliable and valid, both. If possible, choose a manipulation that has been used in the past by other researchers. You want to administer the independent variable in the same way, which you want consistency of treatment, and you want to consider including a manipulation check. You want to ensure that the dependent variable is reliable and valid by using an existing measure or scale, making sure that the measure will be sensitive to the independent variable manipulation. That would be a pilot study. Use more than question or item to operationally define the dependent variable, and automate or standardize the data collection, and use multiple measures to assess the dependent variable. Table 9.1 is a quick summary of what we've just gone over now. A correlational design, a quasi-experimental design, and a simple experimental design. The independent variable is not manipulated on a correlational design, but it is on the other two. And what it tests is, in the top example, correlation and relationship, as well as the quasi-experiment does that as well. The simple experiment tests causality. In figure 9.1, what it states here at the bottom of the picture is cell phone drivers are sometimes distracted. What is the impact of their distraction on other drivers? Does it cause an increase in aggressive driving by other drivers when they get frustrated by people talking on the cell phone while driving? What figure 9.1 leads up to is this practice 9.1. And you are asked to think in your mind about how you would design a simple experiment. So does the use of cell phones while driving increase aggression by other drivers? It walks you through the steps here by asking you questions, and your answers to these questions you can confirm whether your thinking is in line with the author's thinking by going to Appendix A at the back of the book. And it's a very long answer, therefore it's very instructional, so I would recommend that you go into it and test yourself to see if you came up with a good experimental design as recommended by the author. You are not required to read pages 312 to 321. This is talking about the actual formulas in calculating a t-test. You will, not for the purpose of this class, you will never need to understand the formulas of a t-test because we have SPSS software, which I will get into here next. Once again, this is figure 9.2, is part of the section that you do not need to read. And as I was mentioning, you're not going to need to know the workings of this formula for this class here. These tables are also part of teaching how the formulas work. You're not required to learn what's on table 9.2. You're not expected to do practice 9.2 because the reading that you're skipping. And as well, you're not required to understand the actual workings of a confidence interval, although you are expected to understand that confidence intervals of 95% are the baseline in public administration, social science research. Now we get into the SPSS data output. The reason you're not required to get into all of the formulas is because SPSS gives us this. Table 9.3 is a table that SPSS can generate for us. So now at table 9.4, what we get into is we actually get into the outcome as you would see it when generated by the SPSS software. And we're going to talk about these and what these tables mean later. But as you're reading in the textbook, these are back into the sections of the textbook that you should start paying attention to when you get to table 9.3, 9.4, and 9.5. So let's look at practice 9.3 now. This is the test scores based on an interruption by cell phones ringing or based on white noise in the background of an air conditioner running very loudly. And it shows here that the constant noise had less of an impact on test score outcomes than the phone ringing twice during the writing of the test. So this is the outcome, as you would see, coming out of SPSS. But how do you interpret that? Well, you look at the Levine's test score, anything above 0.05, and this is, you're going to read everything that's here in a yellow bubble is something that you're going to read when you actually go to the back of the textbook to test yourself as to how well you did in understanding practice 9.3. And so it goes over 2 or 3 pages, and it's a very long answer, and it tells you why you can reject the null hypothesis, and it tells you about the effect of the Pearson's R and R squared. So these are what I want you to come back to if you have any trouble. Mark this point in the video so that you come back to it. But these are the only sections of the SPSS output that you're really going to have to focus on for the purpose of this course here. And that is understanding what the Levine's test means when it's anything above 0.05, the significance of what P is when the significance level when P is less than 0.05, and whether it's a two-tailed result or a one-tailed result. Pearson's R, which is given as minus 0.372, gives you an R squared, which doesn't show anywhere on this output, of 0.138, or that would be a 13.8% of the effect could be attributed to the distraction by the cell phone ringing as compared to the white noise of an air conditioner. So these are the sections of the SPSS that's going to mean something very significant to you in this class. And what I want to talk about now is what you're going to see in assignment number 5 and how it relates to this module. This is what you're going to see on assignment number 5. This is the output that is expected to come out of your work. And it gives you the Pearson's R, it gives you the R squared, of 0.066 or 6.6% of the effect can be attributed to this variable that we are examining. So now we can look at the output that you're going to be dealing with as part of assignment number 5. The final part of assignment number 5 asks you to do a regression. So a regression is a correlational design study. And what you are comparing in assignment number 5, on this part of assignment number 5, is the correlation between years of education and hours of TV watched in a week. Okay? And so it goes through and it asks, then this is from the General Social Sciences Survey with the GSS.SAV dataset. And the GSS.SAV dataset asks just tons and tons of questions about how many years of education you have, and it asks how many hours, and it studies behavior. And so what you're allowed to do with this huge data set is look for correlations. And once again, you're not looking for any causation, so you're not doing, all you're doing is using their data. You're not designing this study, they designed the studies, and they're just giving you this data. So all you can look at with the GSS.SAV data set is a correlational design. And so we're going to look here in assignment number 5 at how the years of education is correlated with the hours of TV watched in a week. And this is what you come up with as part of the SPSS output when you follow the instructions in assignment number 5. So it gives you the Pearson's correlation here, and it also gives you the Pearson's R. It also gives you the R squared on this output here. The correlation between years of education and hours of watching TV, that correlation alone can explain 6.6% of the effect of TV watching. And then it also, the last piece of output that is useful here as it relates to what we just read in this chapter, chapter 9, is the standardized coefficients, which is the beta score. Now, what that means when you get to this is that you were looking at a predictor and you were looking at an outcome. And how can you tell which one is which? Well, it tells you that the predictor is your independent variable, and what we have been doing all semester is we've been looking at a model where x is correlated to y. So x is on the independent variable side, y is on the dependent variable side. So your predictor is x. So if we actually put this on a graph, the x-axis becomes the predictor. And so we're looking here at the years of education becoming the predictor. So if I look at somebody who has 15 years of education, what does that predict for me as it relates to how many hours of TV they will watch in a week? And so the hours of watching TV become the y-axis, or as it states in this chapter here, the outcome. So we have a predictor and we have an outcome. So what this tells us then is that for every additional year of education, there is a minus 0.257 decrease in hours of television watched. This is where the beta coefficient comes from. That's what a beta coefficient of minus 0.257 means. It means that it is decreasing because it's a negative slope. Remember your years back in math, where the rise over the run equals the slope. So we've got the rise over the run giving us a negative number. So that's a negative slope. So 1 year increase in education is correlated to a 0.57 unit decrease in hours of television watched. So what's 0.257 units when it comes to hours of television? It's about 15 minutes. So 1 more year in school is a predictor of 0.257 or 15 minutes less television per week being watched. So the predictor is on the x-axis and the outcome is on the y-axis, as indicated in what we've studied all semester long as it relates to the modeling. X is correlated to y. That's all we're going to do for this chapter. Everything beyond page 327 you are not required to read. It talks about one-way ANOVAs and other studies which are beyond the scope of this class. And so as it relates to chapter 9, this is it. Do not read anything past page 327.